Okay, so today we have Elias López. He's a PhD here at the Institute, and he will talk about the planetary dynamos in evolving cold gas giants. The floor is yours.
So, thank you. This is a project, one of my main projects of my PhD, and everybody in my group is involved, plus other people. So, ask anything later. Okay. I will first give a brief introduction about planetary magnetism in the solar system, mainly Jupiter, because I will be talking about gas giants. And then I will speak about interior planetary simulations and my planetary simulations. So first of all, which solar system planets have magnetic field? The answer is almost all of them. There are a couple, like the Moon and Mars, that we know that they had it in the past. The others, we have measured them. So yeah, they all vary in sizes and strength and shapes. For example, the Earth and Jupiter are quite similar, are dipoles, that more or less dipoles, but a bit tilted. Uranus and Neptune, they are a bit dipolar, but the dipole is completely misaligned with the rotation axis. So that's why you see these two blobs. And yeah, the Saturn and Mercury are quite axisymmetric. And the only moon we have measured the magnetic field of is Ganymede in Jupiter. So where do these magnetic fields come from? They need to come from a dynamo process. Why? Because there's an equation called the induction equation that tells you if there's no amplification of the magnetic field, which is this term, then this term, which is the diffusion, would kill the magnetic field in more or less 10,000 or 100,000 years for different planets. Meaning that if there was no process amplifying or maintaining the magnetic field, it would have decayed by now. And in order to have this dynamo mechanism, you need to have a conductive and a convective interior. And yeah, for different planets, the nature of the conductive medium is different. For example, for rocky planets, it's mainly a molten iron or iron and nickel. But for gas giants, it's metallic hydrogen. I don't know if you've heard that the existence of metallic hydrogen. And for Uranus and Neptune, it's salty oceans. Okay, what is metallic hydrogen? Metallic hydrogen is hydrogen under a lot of pressure and not so much high temperature. If you heat it enough, it will be like plasma inside a star. If it's not heated enough, this is a phase diagram in the region where Jupiter and Saturn, their interiors are here. They do have liquid metallic hydrogen. This is important because metallic hydrogen is conductive, and the convection of a conductive fluid may lead to the amplification of the magnetic field. These plots are very nice. They are done by planetary people. The actual plots look a bit more chunky and messy. Yeah, but what I want you to remember is that metallic hydrogen starts at around 1 megabar. There's a pressure where metallic transitions from molecular to metallic. So I will mainly speak about the planetary Jupiter's magnetic field, and it's been measured by this satellite, which is called Juno, and it arrived in 2016. And this thing here is the magnetometer. I have no idea how it works, but they used it to measure both the direction and the amplitude of the magnetic field. Yeah, I want you to see here that by the shape of the orbits go much closer around the North Pole than the South Pole. And you will see in a second that the magnetic field is much more better defined on the North Pole rather than the South Pole. So yeah, these are the measurements that they took. Yeah, and notice, and they measured the surface field to be about 20 times higher than Earth's magnetic field. And what do they measure? They actually measured the magnetic field itself, but the data is not published as all the measurements of the magnetic field. The people in charge of these measurements, what they do is they expand the magnetic field as a potential, and they give you constants of G's and H's, which are the coefficients of spherical harmonics, meaning that when you look at these papers, you see a bunch of constants that are like a Fourier expansion, but in spherical harmonic expansion of the coefficients. And they do linear systems within observation and parameters, and the papers of these kinds are long, and the computational time needed to correlate? No, it's the verb. Optimize, yeah. To optimize the spherical harmonics coefficient with the actual measurements, these processes are very computationally expensive. So I'm going to tell you what a spectra is. A spectra is, if you remember from your chemistry long years ago, each of these orbitals have the same energy, meaning that this has the highest energy, these three have the same energy but lower, these three the same energy but higher, sorry. And if you sum all of these contributions, you obtain this spectrum, meaning that this first number would be the energy of this mode. No, sorry, of these three modes, because the magnetic field cannot be a monopolar, cannot have a monopolar contribution. The first energy corresponds to these three modes summed. The second point corresponds to the quadrupolar moment, which is this one. These to the sextupolar moments, and so on. And what I want you to see is that Jupiter and Earth have dynamos inside and have this kind of spectra, falling spectra. But other objects such as Mars, the Earth, and the Moon have like a flat spectrum. And this is only crustal magnetization from a past magnetic field that left magnetic fields in the rocks around the crust. And they are like randomly oriented. That's why it's like white noise. Okay, so they published the Jupiter's magnetic field in 2 papers. These 2 are 3 years apart, but it's important because between here and here, this was they published only the first 9 orbits, and these the 33 orbits, and the resolution of the magnetic field increased quite a bit. So this is what it looks like. I already showed you before. It's around 20 times higher than the magnetic field of the Earth, and it's mostly dipolar. Mostly dipolar means that you see that on the north, there's a north pole, and on the south, there's a south pole, but it's not as quiet as a dipole. And a nice thing, or an interesting thing, is this kind of south pole in the equator. And before your mind runs wild, this has nothing to do with the big red spot. The big red spot is in this zonal jet, which is here, going westward. And the big blue spot, people call it like this, goes to the east, but very, very slowly. Yeah. And I also want you to remember that here you see the biggest jet is in the equator going eastward. I want you to remember that. The biggest jet is in the equator going eastward. And then there's an alternating pattern of jets. Okay, if you're interested in other planetary magnetic fields, there's a bunch of publications with the spacecraft and the people who did the analysis. Yeah, the 2 interesting ones are Uranus and Neptune that were completely misaligned. And the thing is that the measurements are quite old from Voyager. So yeah, and not until at the late 40s, there's a mission plan to reach Uranus and Neptune again. 2 of the most interesting magnetic fields are not being measured at all. Yeah. So a motivation is, surely if there's so many so most of the planets have magnetic field, surely exoplanets probably will also have magnetic field. And instead of measuring magnetic fields with magnetometers all throughout the Earth or with orbiters, people are starting to try to measure them with with radio observatories, and you can ask Simran because she knows way more than this. But yeah, mainly it's a radio emission from classical electrodynamics that you expect like very non-thermal high bursts of it. And in principle, it can overpower the star, and you could detect, in principle, magnetic fields in exoplanets. So some people are starting to, in our group, to make some models for the magnetic field of random planets, meaning exoplanets, of a general gas giant. So I'm going to jump to simulations, and this is going to be a bit more thick. So yeah, what people have been doing is they run 3D computation, 3D magnetohydrodynamic simulations of spherical shells resembling planets. And what they did is they tried to find some measurement, some outputs. Here is the flux, the convective flux with some constants, and the magnetic energy. And they tried to find these constants in such a way that all the simulations fall into the same line. And then they find that also planets and brown dwarfs and rapidly rotating stars are in the same line. Is it brown dwarfs? Yeah. Okay. What do people derive from this? They derive that all planetary magnetisms are in the same fast rotator regime, meaning Rossby number smaller than 0.1. What this means, the Rossby number, you can think of it is how much the planet rotates divided by how many convection turnover times there are. Meaning that if the Rossby number is 1, it takes the same time to rotate once than for convection to go from the inner core to the outer regions. What does it mean that planets are in the low Rossby number? It means that the planet rotates way faster than it convex. This is mostly why planetary magnetic fields tend to be dipolar, because all the movements tend to align themselves with the rotation axis. Yeah, and with these scaling laws, these are called scaling laws, they derive a simple formula, which you can put the mass, the luminosity, and the radius of your object, and you could get more or less what's the magnetic field. Be aware that the uncertainty is quite big. Okay, so my project is involved with how these planetary magnetic fields evolve in time. And with this scaling law, people already gave some estimates of how this magnetic field would decay. And yeah, and this is more or less the scaling law. The magnetic field decays with this exponent in time, more or less. And my project is, can an alternative strategy involving 3D simulations give more information rather than only knowing, okay, the magnetic field is going to decay in time like this, and that's it. So what we did is we used 1D stellar evolution code that evolves stars in time. This is the Hertzsprung-Russell diagram. And if you just put very low masses, you end up with only a giant planet contracting. And that's what we did. And we picked the output of these simulations and we put them in a 3D code. And then we evolved them. Okay, this is how it looks like. Here's the radius of the planet contracting in time. Here's the radius of the dynamo inside, where it starts. And here's the scaling law of the magnetic field, how it predicts. This is T to the -3. And what we're doing is we're picking several different points in this evolution, and we are taking these profiles and putting them in a 3D code. The 3D code does not evolve the structure in time. And the question is this okay? It is, because the cooling time, the cooling evolutionary times, it's about 10 to 100 mega years, meaning that, and the convective turnover time is about 1 and 5 years. meaning that if you take a snapshot and you evolve, I don't know, 300 years, it will almost have not contracted. So it is fine to evolve this structure in MHD without taking into account the contraction of the planet. And we simply take several snapshots of this evolution and try to see what kind of planetary magnetic field do we record. So these are some of the internal profiles. Here are two different planets. One is 1 Jupiter mass and the other is 4 Jupiter masses at 3 different ages. The purple is 0.5 gigayears. The blue is, the dark blue is 1 and the light blue is 10. And you see the planet a bit contracting here. This is the radius and it contracts, and the density increases a bit when it contracts. Yeah, and we use this density, gravity, temperature, and 2 other thermodynamic coefficients that I will not get into. And we put them as polynomial expansions into the 3D code. These are the scary equations of the 3D code, which we use magic. And what I only want you to see is that every time you see a quantity with a rho, it comes from, it's one of these profiles that we take and we put here as an expansion. And another thing that I want you to see is that there are some numbers here that are not the usual rotation, the shell thickness, or the diffusivities. They are ratios of this. And usually people in Dynamo, either stellar or planetary, work with these numbers because it tends to be cleaner. That's one argument. And the other is because some of these parameters, you cannot put the real values into the simulations because the computational needs to resolve these simulations would be unachievable right now by orders of magnitude. So what they end up doing is defining these 4 parameters and try to get as close as they can to the real planetary values. Yeah, and the only radial dependency that we do not use from MESA, the evolutionary code, is this magnetic diffusivity. This we take as an analytical expression that it's a polynomial followed by an exponential decay. Why? Because inside the planet there's a metallic hydrogen which is conductive and the conductivity is high. At some point, metallic hydrogen stops existing and the conductivity decays. Where do we pick this polynomial to exponential decay? We pick the radius where the pressure is 1 megabar. You remember from before, the pressure 1 megabar is when hydrogen becomes metallic. So we go to these profiles. I did not show the pressure, but we go to the pressure. We ask, where is the 1 megabar? And at that point, we go to this formula and put this radius that goes from polynomial to exponential. And you have these different radius for each planet. So we only made 2 further assumptions. That is that the planet rotation doesn't change in time, which some people have argued for. And yeah, they say that after the first million years, mostly the rotation doesn't change if there are no other effects such as migration or other satellites. And diffusivities are constant in time. The diffusivities came here in these Prandtl numbers, they are called. And we assume that these Prandtl numbers are constant throughout the planet's evolution. Yeah, so overall, what do we get from MESA, from the evolutionary code? We get the 1D profiles that we put. And we also evolve these 2 parameters, the Ekman and Rayleigh number, which were, I have it here, taking the rotation and the shell thickness and the temperature. That gives the 1D code, and then we translate their time dependency into here. Yeah, what I want you to see before I show you my results is that here are these input parameters. Here are the values of Jupiter, which are quite big, 10 to the 31, 10 to the minus 18. And this table is from one of the best resolved simulations out there. And the values they use are quite far away from the actual ones. And this is spending millions and millions CPU time. The values I'm using, sorry about this is 10 to the 9, not 10 to the minus 9, are a bit, an order of magnitude less expensive to say, because I throw a bunch of simulations and they only threw one big one, and it's in this paper. So yeah, I want you to keep in mind that the actual parameter space is far apart. So this is how one of these simulations look like. Here is the wind outside, and I want you to see that this jet is in the equator and goes, I will show you in a moment, it goes to the east and it recovers directly the planetary magnetic field. This is the magnetic field at the surface, which is mostly dipolar, but not so much. This one is less dipolar than Jupiter. And yeah, I want you, these two are equator cuts, and these four are meridional cuts from north to south. I want you to see that these meridional cuts from north to south, they show columnar structures. And this comes from the fact that we are in the low Rossby number regime, meaning that the planet rotates many more times than there are turnover times, meaning that all the movements are dictated by the rotation. So the structures tend to be columnar and align themselves with the rotational axis. Yeah. Here we prove that the saturated state is independent of initial conditions, meaning that three models I showed you, the one at 0.5 gigayear reach a saturated state, but they all reach different saturated states. And if we continued, we used the final conditions of the 0.5 megayears and start the 1 gigayear, it rapidly goes to the same place, meaning that it doesn't matter. These simulations are so chaotic that it doesn't matter where you started from. Yeah, and our simulations, more or less, this time scale is about 300 years of planetary convection. Here's how one of these simulations look like. Yeah, sorry. I'm going to show you a video that starts from up here, meaning that there is convection, but there's no magnetic field. And you will see the kinetic energy decreasing and the magnetic energy increasing. And at the end, they both reach a saturated dynamo state. Yeah, here you see the jet, the equatorial jet. And at some point, you will see the magnetic field appearing and stealing energy from the convection. If you want to see the hardcore version of this video, it's this one, which is all the components and all the cuts. Here's the meridional cuts. You'll see columnar structures. Here you see the equatorial cuts. In the equatorial cuts, you can see the jet going around and everything rotating. And here's the same components outside. So yeah, very pretty, but the actual plots give the physics behind. So yeah, here is, for example, the energy distributions in radius. And you'll see the big jet that I told you is this bump in the outside. This is the kinetic energy and the magnetic energy. The magnetic energy is dictated, has a downfall that corresponds to the same place as when the conductivity decays, because it kills the magnetic field. And this is the spectra, which is how the energy is distributed in the different multiples. Here, this kinetic energy zigzag comes from also the jet, because the jet only takes L equal 2, L equal 1, L equal 3, L equal 5. And that's why the structure of the jet makes this zigzag. Okay. Was this the first kind of simulation? Was this the first simulation of this kind? The answer is no. Somebody took some profiles from Jupiter, from a paper, and put them in a 3D code and recovered something very, very similar. And you can see also in my simulations and this one that they do not recover the alternating path jets that I told you before. And this is an issue. And there are some people now that they are starting to try to recover this by adding complexity in these models. And the complexity here comes from a stably stratified layer, meaning that instead of all being convective, they impose a stratification in a part of the radius. And with this additional ingredient, they start getting these alternating patterns. And yeah, so last year there was a model that showed very clearly this kind of patterns. So to finish, this is the magnetic field of the Earth going inwards. We are outside the planet and we're going in, and you'll see this is the magnetic spectrum, and you'll see at some point that it reaches a flat spectrum. Here's at 0.55. You'll see at 0.55 the video will stop, and the magnetic field will be quite complex, and the magnetic spectrum will be flat. And this happens because if you get close to the dynamo region, at the end, this spectrum is flat. And when this spectrum is flat, electrically conducting material has started. And for the Earth, this coincides exactly where the liquid inner core starts. If you do the same for the Jupiter data, you'll recover a radius of 0.8, more or less. But the thing is, for Earth, the liquid core starts sharply, meaning it's a sharp boundary condition. But for Jupiter, it's not. It's a gradual transition from non-metallic to metallic. Yeah, and the question is this 0.8 good enough? And some people in simulations did a study, and they found a better way to define it. And I will show you now. Yeah. And what you have to do is these two things I showed you before, the radial distribution and the spectra, you can express them in a 2D plot. Meaning that if you integrate here, you end up with this plot, and if you integrate in this direction, you get this plot. And what you do is you go to your simulation and go to the outermost region, and you pick this spectra outside. That it should coincide a bit with the spectra outside in Jupiter. And when you do this, you recover these kinds of spectra. And what you do is you go inside and you do two things. You extrapolate from your simulations directly, which are these points, or you extrapolate as I did here in this video. Well, it doesn't want to show. In this video, which is this formula here, that it assumes that there are no currents and you go inside. So in your simulation, you do this procedure, and at some point, the slope diverges. And usually people define the dynamo region when this slope goes to 0, but it's not the same as when the slope diverges. So, and what we did is we picked the definition of dynamo region when these slopes start diverging, meaning the slope from the simulation, which is the solid lines, and the slope of the magnetic field interpolated downward, which is the flat spectrum. Why did we do that? Because the scaling laws from before, they give you a scaling law for the magnetic field at the dynamo surface. And when we pick the values of the magnetic field at the dynamo surface, they align more or less to the same scaling law that I showed you, t to the minus 0.3, which is very nice. Yeah, I will not go more into detail. So we do recover the minus 0.3 time dependence, but we have 3D simulations, and 3D simulations have many more outputs. And what we notice is that there are some transitions. We saw a transition appear. If you see, yeah, this is time, the different simulations in time. And what we saw is that the dipolarity showed a sharp change in two different measures of dipolarity, meaning that some models were multipolar, were more random, and at some point we had a sharp change and we saw mostly dipolar dynamos. This happened in time. Yeah. And you can see that not only this, but some other magnitudes, such as, I will not go into this, but the fraction of atomic dissipation or the Elsasser number, tend to change behavior when things are multipolar and go to dipolar. They change behavior here, and also here, and also here. They have a change of something changes inside, which is like the force balance inside the simulation. People have studied multipolar and dipolar dynamo branches, and they see that the force balance inside is slightly different. So this makes sense. Yeah. And there was one nice paper that they simulated stellar dynamos, and they saw that if you changed a bit the parameters, you had like a clear distribution between multipolar and dipolar dynamos. And we did the same for our models, and the bigger models correspond to early ages, and it wandered around here, and at some point it jumped there. So this was a nice plot to see that, yeah, we are seeing a transition, which can be understood a transition in time. And is this expected? Yes, it is. Because if you see the distribution of where dipolar and multipolar or dipolar dynamos are, here is the Rayleigh number. The Rayleigh number is proportional to the temperature difference, meaning that here the convection is more vigorous. And if you go down there, the convection decreases. If you simulate a planet in time that it might start in the dipolar regime, the Rayleigh number might decrease, and then it jumps to the dipolar regime, which is what we're seeing. Yeah. Am I claiming that all planets go from multipolar to dipolar? No. But if you take Jupiter and Saturn as the average gas giant, they are both dipolar, meaning that maybe the planets start in the dipolar regime and end in the multipolar regime and end in the dipolar regime, or maybe they are directly born in the dipolar regime and stay there. Yeah, here's another plot that we did. We varied Prandtl numbers a bit, and we saw, I won't go into this because it's awful. But we saw the same behavior. So yeah, this was just a check to see if we change Prandtl numbers, do we get the same time dependency? And the answer is yes, we did. Yeah, and the last couple of slides are, here's one of these scaling laws that I showed you before. And you see here the Rossby number and the convection power. As I told you, these are all simulations. The actual planets would be more or less here. And you cannot reach them because the computational needs would be a million times what we have now. Yeah. And what we did is we picked our simulations and we plot them inside this plot, and that's what we obtained. That's how much one of our planets evolved in time, meaning that they evolved downward and about 1 order of magnitude. So the actual planets are not here, they are down there, but this is how much you should expect one planet to change in this parameter space in time. Yeah, and this paper that they do this scaling laws, they also have other scaling laws related to magnetic field, and these scaling laws are different for the multipolar branch and the dipolar branch. And our results, as they do, some of them are in the dipolar branch and some of them are in the multipolar branch. And yeah, our longest set of runs, this blue one, jumped from multipolar to dipolar. And some other sets with different Prandtl numbers, they simply stayed in the multipolar or simply stayed in the dipolar branch. Yeah, and this one is another measure that was quite more clear, the difference between multipolar and dipolar. Yeah, and we saw this trend from going from a multipolar dominated region to a dipolar dominated region. Yeah, this is the magnetic dissipation timescale in the simulation. So as a conclusion, we used 1D evolutionary models for gas giants, and we put them in a 3D code, and we obtained dynamo solutions for them. And we obtained like the strength of the magnetic field agrees with scaling laws. We show that multipolar and dipolar dynamos behave different in time, and there's a possible transition from multipolar to dipolar. Yeah, and these trends could also be applied for brown dwarfs and slightly irradiated planets. Yeah, and right now we are applying the same kind of logic for hot Jupiter profiles, and these hot Jupiters are different because they are highly irradiated, and their rotation is not free because they are tidally locked. Yeah, and what we also have in mind that we can do is we assume both diffusivities to be constant in time, and we might put a time dependency, a physical time dependency from them. And we might also, like I showed you, these stable stratified layers. There are a couple of codes that are starting to add these stable stratified layers in their evolution. And we can ask, they are not public, but we could ask the people for these codes and get these stable stratified layers into our simulations. Yeah. Yeah.
Okay, nice presentation. Thank you. Are there any questions, Robert?
Thanks for the presentation. Maybe you said it, but I kind of missed it. So the jet that you get at the equator is something that develops in the simulation of systems,
yeah,
just with the rotation, and how can you kind of have a say in the way this is shaped, where you put your initial conditions?
Yeah, I didn't put this one. Okay, yeah, let me. Yeah, you can see it here. Usually, it's due to the boundary conditions. Usually, if you simulate the Earth, you assume that the velocity here in the inner core is 0, because there's a solid core, and it doesn't allow the fluid to move. And for the Earth, you also assume the same outside. And the simulation does not develop jets. But for gas giants, there's no boundary outside, and you let the outside surface free. It can have the horizontal velocity, it can be whatever it wants. And by itself, it develops this jet.
So by itself, you mean also due to the rotation of the planet itself?
Yeah, yeah. In the equations, there's the rotation term, which is here. If you take it out, there's, yeah, if you put the Ekman number very, very high, you kill rotation and you don't get it. It's a completely different solution.
You showed, I think it was on your slide 10, you showed the spectra, right? Yes. So you said that for Mars and Moon, right, there's like no active dynamos, so whatever you have is like rocks.
Crustal,
so it's like noise,
yeah.
right?
Yeah.
So the same would go for Earth, right? So at some point, like the slope,
yeah,
and then it like whatever is like residual in like rocks or whatever.
Yeah.
And so okay, so I understand that. And the question is for Jupiter, right? I only see like.
Yeah, this plot is very old. I didn't want to show the actual plots yet.
Okay.
Yeah, right now this plot is filled until multipolar 18, which is more or less here.
Okay.
Yeah, I didn't say that. We can only see Earth's dynamo up to multiple 13, yeah. Because over that there's crustal magnetization that is more powerful than the actual dynamo itself.
So and for Jupiter.
For Jupiter, it reaches 18. So actually, the best measured dynamo is not Earth; it's actually Jupiter.
Okay.
Yeah, I didn't say that. I forgot.
Okay.
More questions?
Another one, maybe, and you kind of introduced it yourself. But if you wanted to do a simulation like this for the Earth or a rocky planet in general, I guess the issue is that the 1D profile becomes a whole other job to do. But,
Well, yeah, actually,
are people doing this?
Yeah. This is called, I didn't go through. This is called the anelastic approximation, which is the 3D MHD code. It's almost not compressible, meaning that you allow radial dependency, but you do not allow this radial dependency to change. And for Earth-like dynamo, what people use is the Boussinesq approximation that they assume the density to be constant. And usually all these profiles, radial profiles, get erased. There's no radial dependency. And the solutions are a bit different. Not that much.
Is there any way we could detect the initial B field that was accumulated during the formation of the planet?
Yeah, this was a question of the referee, actually. Yeah, there's a couple of planets. There's a couple of planets that are young and close. One of them is Epsilon Eridani b. And yeah, we given this one is the closest and most probable to see if this initial multipolar thing is real or not. And yeah, it's the first detectable object that we could have. There are no planetary magnetic fields that detected yet, but hopefully with the SKA, when it opens fully, something will come up.
Okay. So you say you want to detect magnetic fields of exoplanets, but then you say that for Neptune and Uranus don't have data. But I mean, if you can do it for exoplanet, you can do it.
Yeah, but we are trying to detect radio emission.
Somebody could think about an experiment. Maybe the wavelengths or the frequencies are not right, or whatever. I don't see why you can get much.
Because yeah, this instability actually depends a lot on the strength of the magnetic field, and actually gas giants are the strongest ones, and probably this will be first detectable for gas giants. These kinds of non-thermal bursts. I don't know. Maybe Simran could answer these questions rather than me.
You are below the ionospheric cut. So the Uranus emission, you can get it, but you have to go to the upper space to see the frequency, because the ionosphere blocks whatever is below 10 megahertz. No, because it's blocked. You don't have any radiation below 10 megahertz because of the ionosphere. You don't see the sky below 10 megahertz. From space? From space, yeah, but you need to.
A radio observatory.
So you just better to go there and try to have a physical measure.
I mean, it's cheaper to do something on the Earth.
Maybe on the moon. But people are thinking about that.
Yeah, so you mentioned in your future work, right, you want to look at what Jupiter's, which makes sense because those are the planets we find the most, right? And they're tightly locked, and there's like a lot of NASA things going on. But you would also expect the magnetic field of the star and the planet to interact, if they're that close, like to have a shared magnetosphere, whatever. So
yeah, we're not taking that into account.
Okay.
We are only simulating the interior.
I feel like there was someone that I met like years ago that was looking at a system like this. I need to find it. So there was they showed some observations of like a star and like a close-in planet where they simulated sort of the shared magnetosphere and mass transfer and all of this stuff. But
I think these kind of simulations also assume a dipolar stellar magnetic field and a dipolar planetary magnetic field. Because probably these the magnetosphere simulations, they do not know the actual shape. They make assumptions.
Yeah.
And I wouldn't know how this would work. How you could impose. There's a way to impose, actually, outer magnetic fields. I could look into that, actually.
So one question, so in Uranus and Neptune are conditions, so who is driving the dynamo there? So are conditions enough for having also metallic hydrogen?
There are metallic hydrogen conditions in the inner core, but they have like a salty oceans outside. And people do not know if maybe the salty oceans are doing something weird to the dynamo inside, or maybe it's the actual oceans that they do like a very weak kind of weird dynamo. It's not known, actually.
And the idea that it's not an anti-rotation axis, but if confirmed by better measurements, could be the risk.
Probably it's the salty oceans. Either they are doing something weird to the magnetic field, or they are generating a weird. I don't know. Yeah, I don't know. My guess is that salty oceans are not enough, but I wouldn't bet on it.
We can check if there's any questions in the chat.
No.
So, final question, anything else? If not, let's thank Albert again. I'm actually not sure where the pizza is going to be.